Hi guys, today we're going to talk about projectiles fired at an angle. We've already done three types of projectile problems. Free fall, which is the first picture. Vertically fired object is the second picture. We talked about horizontally fired object problems last week. And now we have the last type, which is projectiles fired at an angle. So we're going to go through the problem solving process here in just a minute. So the typical setup of these problems is this. You're given the velocity and angle, and the object is fired and follows a parabolic path. It goes through the whole motion here. So points A, B, and C like we did before. Now maximum height is going to be point B. It's the highest point in the middle. So the first thing we do when we solve these problems, which you're going to be given the velocity and angle, is you take, and I'm just going to draw up here, you have this velocity at an angle. And we have to break this velocity up into parts or components. So you're going to be given the velocity. You have to break it up into the x part and the y part. So how we do this is we have to use a little bit of trigonometry. So in order to get the x part, you could use cosine. So katoa. So use cosine equals adjacent over hypotenuse. That's supposed to mean theta equals adjacent over hypotenuse. Now if I plug in what I need to what I have, cosine of theta equals Vx over Vi. So Vx equals Vi cosine theta. I could do that for the y part of the velocity, and I use sine, and I end up with these two formulas. Vx equals Vi cosine theta, and Vy equals Vi sine theta. So the question comes up, do I need to memorize these? The answer is no, however, you're going to be using them. And if you want, if you forget, you can use your reference table. So if you go to your reference table, you flip to the back page, you have these formulas. So if you look at these two formulas, AY equals A sine theta and AX equals A cosine theta, that's A represents any vector, so you're going to be using these. So Vy equals V times sine theta and Vx equals V cosine theta. So now it's the same idea as what we've done all of these projectile problems. When we get to the top, the x velocity is constant. There's no jetpacks on the sphere or the ball or whatever is projected. And if you remember, the y velocity at the top is 0. So that's an important hint. So now, as we get to point C, the projectile goes back down. The x velocity is still constant. And the y velocity, if you remember, is the same as the initial y, except it's negative. So the y velocity is a negative of the initial y velocity. Just like in the lab we did, let's say the initial y velocity is 7. The y velocity when it gets to this point is negative 7. And the total displacement at this point C is 0. This hint we rarely use, but it's good to know. So there's some hints that are going to help you solve these problems. One is that the acceleration is still gravity. It's negative 9.81 meters per second squared. The second one, let's say it takes 3 seconds to get to the top. It's going to take 3 seconds to get down, and the total time in the air is 6. So time up equals the time down, and then the time up is half of the total time. So to give you a visual of what's happening, let's check out this animation. So I am going to fire this sphere, and just notice what happens to the x and y velocity. So as the sphere is going, you can see the x velocity stays the same the whole time. The y velocity gets smaller and smaller and smaller. At the top, the y velocity is 0, and then it gets bigger and bigger and bigger in the negative direction. So this, like I said, this is a typical setup for projectiles at an angle. And what we're going to do now is we're going to go through the classic problem. So imagine you have a cannonball, fire from a cannon with initial velocity 100 meters per second and an angle of 30 degrees. So the first part you always do, if you get the velocity and angle, is you break the velocity up into parts, into components. So I'm going to draw the picture here. 100 meters per second. This is 30 degrees. So we have to get the x velocity and the y velocity. And if you refer back to the last page in your notes, that last slide, we can get Vy equals to Vi sine theta. That equals to 100 meters per second sine of 30 degrees. And if you have to show work, the degree symbol counts as your unit. So we have to use our calculator. We get 50 meters per second. So we find the x component by using the formula we got on the last page. So we do 100 meters per second times cosine of 30 degrees. If you take your calculator out, which you should have it out, don't just watch me do it. And if you didn't get the right answer on the last one, by the way, make sure you're in degree mode. You get 86.6 meters per second. Now, one extremely important item here is that when we do these problems, once we break the velocity up into parts, into the x part and the y part, we're not going to use this velocity and angle anymore. So that's really important. The next couple of problems we're going to do, you just use the parts, not the velocity at the angle. And that's the most important step in these. Now, time in the air. If you think back to the projectile at an angle, vertically fired projectile problems, we found time in the air knowing that at the top, at point B, the y velocity is 0. So I'm going to write that hint down. At the top, Vy equals to 0. So I can use this formula like we did. This is exactly like the vertically fired object problems. So we do Vf equals Vi plus At. Now we're going to be using y information, so I have my little subscripts. So the y velocity at the top is 0. The initial y velocity is 50. And then gravity, the surface of the Earth, negative 9.81. So if we solve, we get time equals to 5.1 seconds. Some rounding. Now, this is a common question. So you get the time. When we found the time, this is at the top. So this time is a time to the top. So in order to get the total time, which is what we want, we have to multiply this by 2. That was a common mistake people made in the test. Total time is double the time to the top. So there we go. So now for max range, it's still x information. And if you remember, there's only one formula in the x direction that we use. And that formula doesn't change. V equals d over t, or d equals vt. And since we want x information, we're going to use our x values. So if you look back at the last page of your notes, the x velocity is 86.6 meters per second. The time in the air is 10.2 seconds. So we use this information and solve. And if we do this, I'll give you a minute to use your calculator. You get 883.2 meters. That's how far we've gone. So the last problem, and like I said, this is the typical setup. So you're going to be doing this setup for all these projectile and angle problems in a future lab. So we want to know the max height of the cannonball. So the maximum height, we want y information. And now we know, just like in problem B, I'm going to write it again. At the top, the y velocity equals 0. So I try to use the easiest formulas I can. So what I'm going to do to get this one, I'm going to do Vf squared equals Vi squared plus 2At. And like I said, I write these subscripts so I don't get my information confused. So at the top, the velocity is 0. I'm just going to write myself a hint. The initial velocity, we had got the initial y velocity, and that's why I have the little subscripts. So if we do this, and we solve, and make sure you do your algebra right, you get, it goes 127.4 meters up. So, as I said, this is a classic projectile and angle problem. So if you follow this process, you'll be able to do any projectile problem we get in class, on a quiz, on a lab, on a test. So please try the problems I assigned. The next 2 pages, the intro to projectile problems at an angle, and we'll talk more in class. Have a great day.